All right, let's get started for today. Let's see. Logistics. Your homework 1 was due yesterday night, but you can use late days. Maximum late days for one homework is 4. So by Saturday night, it's absolutely due, and you have only 7 for the semester, so don't use them all 4 of them maybe if you don't have to on the first homework. Some people are asking how long can the homework take? Our estimate from last year is 20 to 40 hours is pretty common. If you do it faster than 20 hours, it'd be quite rare. If it takes more than 40 hours, it's not uncommon. If it takes 100 hours, come and see the TAs more often, because that's definitely not the intent. But a couple of new things this year that I'm very excited about. So your homework will be due on Saturday for the people who are late. Then Sunday or Monday, one of those days, we will publish our solutions. So you can actually compare what you did with what the TAs did to solve the problem. And maybe you can even tell us that you have a better way of doing it. We'd love to hear from you. And when we release that, we like to learn also. I'm sure between the 80 people in the class, somebody's going to have something done better than the TAs did it. So let us know. And the other thing we're going to do is set up a place where you can link yours, if you like to share yours, with other students in the class, and we'll make a post and you can link yours so people can check out each other's solutions, which might also be interesting to learn from what other people did. And the TAs can also look at people's solutions because you submit them, but also on your GitHub or wherever you host them when they're publicly linked. And maybe we can do some kind of roundup and say, hey, here are some interesting things that people did in the next or next lecture. All right, so that's homework 1. Then homework 2 will go out hopefully tomorrow. We'll see if it happens, but our plan is no later than Friday, so you can enjoy your weekend to the fullest with the homework available. It's a long weekend, so extra joy. And then other logistics, let's see. It might be a good time to start thinking about your projects. So your project proposals will be due in a little over 2 weeks from now. And so it might be good to start thinking about that. In 2 weeks from now, you'll also have seen latent variable models. You'll also have seen GANs, which you'll see next week. And so you'll have seen the 4 main types of models. And hopefully that allows you to get some inspiration, think about what you want to do. Questions somewhere? No? OK, any logistical questions? All right, let's dive into lecture 4, technical content, latent variable models. So, oh, by the way, the slides are posted on Piazza as of 2 minutes ago. So if you want to follow along the slides on your computer or your iPad, they're available. They're still going to change a bit, but they're close. We've seen autoregressive models and flows. And in those models, in some sense, all the variables were observed, and we were not thinking a whole lot about latent variables, and that's going to change now. In flows, you kind of have latent variables, but it's kind of strange at the same time because you need to have as many latent variables as observed variables, so there's a kind of one-to-one dimensionality correspondence, and we're going to start moving away from that, have latent variables that maybe could be more abstract, where there's maybe less latent variables than observed variables. So on the left, you see a network, a simple BaseNet autoregressive model with 3 variables, and all 3 are observed, and that's all you worry about in an autoregressive model. But on the right is the kind of thing we'll cover today, which is models where there's a variable z that we never get to observe. It's not in the data ever. There's only x in the data, but we're going to posit nevertheless that there is a z underlying the process of how the data is generated. You might say, why would you do that? The reason to do this is because you might think that under the hood, there's a relatively simple process. You might have a megapixel image, which is 1 million variables or 3 million if it's RGB. But under the hood, there might be a relatively simple process that can be described with less variables. And so that would hopefully then somehow be learned to show up in Z. So what's an example? Look at this picture here. It has some object. Object 1 is a corgi that has a red and white fur. Object 2 is a corgi with red and white fur and a floppy left ear. Then object 3 is a corgi that's tricolor rather than 2 colors. And then the background is some wood, a bench in a park. And so what you see here is, in the bubbles, very short descriptions that capture, in many ways, the essence of what's in the picture. And so the hope, and I'm not saying anybody has actually fully realized this with their latent variable models, but the hope with latent variable models is that maybe we can recover something like this. You give it enough pictures of dogs in parks, and at some point it finds latent variables that correspond to objects in there, objects being dogs or benches or maybe trees, and they have meaning that things that we associate meaning with, which in turn might allow the system that reasons on top of that to be more efficient than a system that directly works with pixels. Okay, that's the motivation. Today's going to be a lot of math, so I want to make sure you're motivated with these 3 corgis, because it's going to be more math than any other lecture we'll do, I think, in this semester. But useful math. So why latent variable models? Well, part of it is latent structure, but we can also think about what are some limitations of the models we've seen so far. Autoregressive models are slow to sample because all pixels are assumed to be dependent on each other. You need to sample the first pixel before you can start sampling the second pixel, the third one, and so forth. So a 1,000,000 pixel image requires 1,000,000 iterations through a network. We can, with latent variables, we can make part of the observation space independent of each other, but conditioned on some underlying structure. So you don't make things fully independent, but you make an independent condition on underlying structure. And once you do that, you could sample first those latent variables, and then from there maybe sample everything else and do it in 1 forward pass instead of 1,000,000 forward passes for a megapixel image. So sometimes it's actually possible to design a latent variable model with an understanding of the causal process that generates your data. So maybe you know that you're working with a graphics engine, and all the data you collect is going to be either spheres or blocks. And the blocks can have 2 sizes, the spheres can have 2 sizes, there is 3 colors available, and there's a table, and that's it. And then you could know under the hood, well, those are the latent variables, the coordinates, which balls I'm going to show, which blocks I'm going to show, in which color, and in which location. That's enough to describe the scene. And that might just be, I don't know, 20 variables, but you render a megapixel image from that. So sometimes that's going to be the case, and you might be able to design that latent space. In general, though, we don't know what the latent variables are and how they interact with observations. They're going to be variables that we want to make very little assumptions about, but somehow, through how we design the network, we're going to assume some notion of simplicity effectively. And we hope that somehow the simplest structure of the world is going to emerge in those latent variables, and it's going to be good to work with for other things in the future. But that said, going back to the first bullet point, if you do know the latent structure, you could, in principle, and that might be a research project, say, hey, I know the latent variables are going to have these and these and these meanings. I want to build a model where even if I can't measure them, I want them to have those meanings, and I'm going to set up an architecture that essentially says, this is going to be a coordinate variable, this is going to be a color variable, and this is how they're going to be combined in my neural net to render an image. You could do that and maybe be more data efficient, but at the risk, of course, if your assumptions are wrong, that you can't model data that doesn't satisfy your assumptions. So the latent variable model that we'll be working with a lot is extremely simple to draw, shown here, z to x. But keep in mind, under the hood, z will typically be a vector. It will not just be one variable, it will be a vector valued variable. And then x will also be a vector, maybe 1,000,000 pixels, something like that. What's a very simple example? Maybe z could be a vector of capital K Bernoulli variables. So every entry in z is either 0 or 1. And for each entry, there is a probability, beta k, of having a 0 versus a 1. And so with this model, you could say, okay, to find my vector z, if you want a better seat, there might be some chairs in the rooms next door that you can pull in and put in the back of the room here. And you might want to take a quick look, or outside. So we can very easily sample z. Just coin flips, biased coin flips for each z. We get our string of 0s and 1s. And then after that, there's this p theta x given z, which let's say could be a neural network that processes z into a bunch of outputs, one output for each coordinate of x, and each output might have a sigmoid, and so it might output a probability between 0 and 1, and then you flip a coin with that probability, and out comes your x. And so that's the model we're putting forward here. Just one example. Another very popular one will be where z comes from a Gaussian, and then x might actually also be continuous or might be a softmax over pixel value or something like that. Any questions about what we have here? Because this is going to be, I mean, the next 2.5 hours are going to be all about doing calculations with this model. Yes?
Would you want to pick a z that has high entropy?
So good question. The distribution for z, what do you want? So we could posit a distribution for z, or we could learn it. Now in today's lecture, we're going to mostly posit it, and we're going to actually posit high entropy distribution. So it's going to typically be a Gaussian, which is for continuous variables with finite variance, the highest entropy distribution you can have. But in principle, you can also learn it. And at the very end, we'll also see ways to learn the prior over z. And you might also want to design it in some ways. You might say, hey, I know that there is discrete effects and continuous effects. And I know that some discrete effects take on 10, imagine MNIST. You say there's 10 possible digits. So I'm going to have a discrete variable that can take on, that's a 10-dimensional one-hot vector that hopefully will capture what's the digit that's being rendered. And then maybe you have some continuous ones that are like maybe the thickness of the pen stroke you hope would show up in there. I'm not saying it would show up, but you could hope for it. And so if you want to solve a specific problem, you definitely want to think about what might be some latent structures that are meaningful. And you might want to choose that prior, or you might fit it to the data also. Other question here.
So do we choose the betas, as you said, like we posit betas, right?
Yeah, so that's in many ways the same question. So for now, let's assume we choose the betas. For most of the lecture, we'll assume we choose beta ahead of time ourselves. And towards the end, we'll also see that we can learn it.
Do we always assume that every element, like every coordinate is like Bernoulli, or like?
This is just an example latent variable model where the z's are all Bernoulli variables. You could have other ones where there is some one-hot encoding subset of z that is not Bernoulli, but essentially a softmax type distribution. And you could have subsets that are maybe Gaussian. You could have them all be Gaussian. The most common case, traditionally speaking, for the models we'll look at is to have a Gaussian for z. Joint Gaussian. Mm-hmm. But we'll also move away from that. The state-of-the-art models today actually don't anymore use a Gaussian. So, yeah. So what do we want to do with this latent variable model? We want to sample, like we've done with all our generative models. Actually, when we're given the model, we're assuming these things are set, because PZZ is associated with this node, and then P theta x given z is associated with that transition. And so if we're given a model of that structure, well, maybe we don't have the right theta such that it generates the samples we want, but for whatever theta we're given, we can go through the sampling process. We can sample, assume we pick a convenient distribution for z, like a Gaussian or uniform or Bernoulli. We can conveniently sample z, and then from there conveniently sample x given z if we set it up that way. And that'll be pretty much a recurring assumption. What we'll do, we'll assume we set things up such that pz is easy to sample from, and p theta given x and z is easy to sample from. And so that'll in some sense constrain a little bit the architectures we're playing with, but we'll see it's actually not very limiting in practice at all. Then evaluating the likelihood is evaluating this quantity here. You have a sample, some data point x, and you now need to look at all possible causes, underlying causes z that could have been happening first. And then for each possible underlying cause, what's the probability of it causing that particular x? And so you have a summation over all possible values z can take on, p z z times p theta x given z. Then to train, well, we're going to do the same thing again. Maximum likelihood, it's a well-established principle to find a distribution when you're given some data. So we'll train with maximizing over all choices of theta. This quantity, the sum over all data points I, log probability of that data point xi, and under the hood, there is another summation here, sum over z, because it could be multiple different underlying causes that result in that particular xi. So these two things both have a summation in them that sometimes will be easy to deal with and most of the time will not be easy to deal with. And most of our lecture today will be about how to deal with that summation over z that's inside the log. Then representation-wise, well, if you think about representation learning, you really want to go the opposite way. If you think z is the compact representation of what you're seeing in your image or maybe in text or speech, well, then you want to go from that text, speech, or image back to z. So you're going to go the opposite way. That's actually not present here. We're not given the opposite direction calculation. Now, we of course know that in principle you can apply Bayes' rule, which when you have the distribution for z and x given z, you can apply Bayes' rule to flip that around. But it's not just because it's easy to sample from pz and easy to sample from p theta x given z that it's easy to apply Bayes' rule and go the other way. And so again, a lot of lecture will be about how do we go the other way in a tractable way, but maybe approximate. All right, that's our problem setting. Any questions about this before we start solving these problems? Okay, this is our full outline. We've covered motivation. Now we're going to look at how we can train latent variable models. And this will include the VAE, the variational autoencoder, and the IWAE, the importance-weighted variational autoencoder. Then first we'll look at the objective we'll optimize. We'll see that we'll need approximations. We'll look at how to optimize, and then we'll look at variations. That'll be towards the very end. This will be the bulk of our lecture here. Yes?
On a high level, how does this relate to flow models?
So the question is, how does this relate to flow models? So in flow model, we also had a mapping from z to x or x to z. And in fact, we chose the mapping to be easily invertible by design, which is nice because then a lot of the questions that we have here were quite readily resolved. We knew how to train. We just needed log determinant terms and so forth. We knew how to go from x to z, even if our model was initially z to x and so forth. The one thing with flow models is that they assume the dimensionality of z and x are the same. And so that's a somewhat specific assumption that often you might not want to make. You might think that there is a latent structure that's lower dimensional than your observations, and then z and x having the same dimension is not great. Of course, in your flow model, you can have your flow only take a few steps for some z's and more steps to recover other z's, which are maybe deeper latent structure. But ultimately, you have to still end up with as many z's as you had x's to make it work. And so you can think of flow models as maybe a special type of VAE where some things are easier to do, but also limit what you can do in terms of architecture. Okay, objective. Our training objective is this thing over here. So, scenario 1. Z can only take on a small number of values. So z has to be a discrete random variable at first for that to be the case, and with a small domain. So maybe it can take only 10 values, something 100 values. Then actually, this exact objective is tractable. You can evaluate this objective, and we know that once we can evaluate an objective, assuming the functions are smooth, we can also backprop the other way, compute gradients, optimize this objective. So we're in good shape. Scenario 2 is where z can take on an impractical number of values to enumerate, in which case we cannot exactly evaluate this, and we're going to have to make some approximations. You might have a question, how about optimizing PZ, which is called learning the prior, and it's sometimes done. More about that later, but let's ignore that for now. Okay, so we're going to now go from exact to something called prior sampling to something called likelihood importance sampling, and then we'll look at the variational lower bound. So let's look at an example where we can do it exactly. Imagine z can only take on 3 values, a, b, c, each with probability 1/3. And let's say x given z equals k is a multivariate Gaussian with a mean determined by the choice of z and a covariance determined by the choice of z. Then if we want to fit our data to this model, we assume a model structure. Now we have some data. We can look at our data, maximize the log probability of each data point. The log probability of a single data point will be a sum of 3 terms, each having a prior probability of 1/3 causing that data point, and then times the probability of that data point given the specific mode that you're in. So what would be an example? If you had a mixture of Gaussians, and up here is your training data. And you might say, well, let's train a mixture of 3 Gaussians to this training data. And after 0 epochs, just initialization, you have 3 means and 3 covariances for each of the 3 modes. And then you just run an optimization on that objective. You just have an objective, feed it, get the gradient, stochastic gradient updates, SGD, and as you go along, you see you actually find 3 Gaussians that nicely cover the training data. Yes?
Is this the same as training a autoregressor? It's just parameterized as 3 Gaussians?
Is it the same as training an autoregressor? If you have a very expressive output on your autoregressive model, you could have an output that has this type of behavior. You could have a mixture of Gaussians output on your autoregressive model for, let's say, if you had, let's say, the next 2 coordinates have a mixture of 3 Gaussians as your model you put there, then effectively in the inner loop of the autoregressive model, you'd be training something just like this. And that's how this would appear in an autoregressive model. What we're interested in here is somewhat going the other direction. Rather than, even though the example is in 2D, it's just an example to showcase that in principle we can do it in low dimensions, but we now want to take this to very high dimensions where this is not going to work anymore. With an autoregressive model, we would split it up. Each variable would be trained conditional on the previous variables, and here we're going to jointly train a model for all variables instead of one at a time conditional on all the previous ones. But you're absolutely right. For the 2D case, here, if you had an autoregressive model, 2 outputs in one stage, you could have a model that's a mixture of Gaussians. By the way, it doesn't have to converge that nicely. It's possible that you get stuck in a bad local optimum that doesn't find the 3 modes the way it found it here. That can happen. You do a few new random initializations, and you see which one has the better likelihood score. So that's a simple scenario. Now, if z can take on many values, then this summation here we cannot evaluate exactly. So what we can do instead is actually use a sample estimate, because it's an expectation. It's an expected value where our expectation of our values that z can take on of this quantity over here. So we can sample our z's, and then after we sample, this term, of course, disappears because that's the density that determines how we sample. And once we have sampled, that's incorporated by our samples. And so they're all now weighted as 1 over k. And then we sum all of them, and the term that comes behind here is matched up. So for every xi, we will sample capital K z's. So z has a double index here because for every xi, we'll be sampling z's. And they don't have to be the same samplings that we do for each xi. Once you've done this, you can run SGD on this approximate objective, and again, you can fit a model. So that's convenient, or it might look convenient, but we'll now look at some limitations for this. Consider your data is in n clusters. So let's say you have some data that's over here, some other data over here. So you have a bunch of clusters. Now, we sample z uniformly. If we have n clusters, z is essentially underlying is the mode that we're thinking about at that moment that x is going to be generated from. Well, in this case, there is 11 modes. And imagine we've already started to fit some Gaussians. And maybe we have a Gaussian living here, one living here, 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 maybe one here, and so forth. Well, when we sample our z, we're selecting one of those modes. But imagine our x is this specific point over here. That's our xi. And we sample a z over here. And we sample a z over that lands us with that mode, another z with that mode. Now all of these are Gaussian, so they spread out infinitely far, but they're very, very low value once you're far away from the mean. And so this sample is wasted. This z is wasted, this z is wasted. Only the z's that land around here in that mode or maybe a very nearby mode will actually contribute to the objective. So go back to this objective here, the sampling objective. What's happening is that this term here, for most z's, this thing will be roughly 0. And in fact, for most z, the gradient of that thing will also be roughly 0. And you learn nothing. And you might say, well, who cares if I need to waste 90% of my samples? I just run 10 times more computers. Maybe you're okay with that. But in high dimensions, it's going to be a lot worse. Because imagine high dimensions, if z is somehow thinking about, am I going to put 3 corgis or 2 corgis? Am I going to put a bench in the back or not a bench in the back? Am I going to put a tree there or not a tree there? And so forth. And you have maybe 100 variables that you pick that characterize your scene. Let's say there are 100 binary variables that characterize your scene. Then you have 1 over 2 to the 100 probability to sample that z correctly to match up with your scene. If you sample it incorrectly, you will not get much learning signal. So once you have a 100-dimensional latent space, 100-dimensional binary latent space, so 2 to 100 possibilities, well, you have very low probability of getting anything meaningful into this objective. So it's not going to work. Because you got to be incredibly lucky, and that's not going to be consistently true. Yes?
Can't you use the same z for all your x's? I feel like still be unbiased estimate.
Can you use the same z for all x's? You can if you want to. I don't think there's much reason to use the same, and soon we'll transition to something where you definitely don't want to. So it's probably easier to think of it as you just resample it, because that's what will happen as we improve this. But for the prior sampling, you can definitely not resample z. It'll work too. Just a little reason not to resample. Z tends to be easy to sample. It's not that z is hard to sample, it's that it's hard to sample a z that actually leads to a meaningful term over here.
I feel like one of the z, for every given z, you should be close to one of the data points, right? Because it's like the xi's are in a high probability region, and the z's should also be in a high probability region.
Not necessarily, because often the underlying z is factored in some way. And so imagine you have 100 properties. And so that might mean you have, in some sense, 2 to the 100 possible scenarios. And assuming your z is uniform, so because you don't want to learn another maybe complicated autoaggressive model under the hood that will be super slow to sample underneath. So this one might be one where the z's are independent, but in your real distribution, your z's will not be independent. In the real distribution, maybe whenever there's 2 corgis, there's always a bench. I mean, probably not, but I'm just making something up. Whenever there's a bench, there's always a tree. But in the underlying PC that you use, typically, you don't have that structure. And because you don't have that structure, you're going to be sampling somewhat uniformly in prior sampling from all possible scenarios of z under the hood. And so as a consequence, just 100 latent different causes could lead to 2 to 100 different things, which is going to be bigger than your data set. Because this is going to be, 2 to the 10 is 1,000, so it's going to be 10 to the 30, which is going to be bigger most of the time than your data set. And so you're not going to have a one-to-one mapping there where for every x there will be a good z, for every z there will be an x in your data set. Yes?
The prior sampling equation you have in the
Mm-hmm.
slide after, should it be pz of z supply instead of 1 over k?
So the question is, why is it a 1 over k over here and not the probability of z? And so the reason is because the sampling process draws from pz. And so because you're sampling according to pz, it's incorporated. And if something's more likely, it'll be more such samples. And they'll each have a 1 over k, but it'll be 5 times the same thing that has a 1 over k, together 5 over k. Okay, so since we can't count on prior sampling to land us in the right z's, what can we do? Well, there's something very general called importance sampling. And here's the motivation. We want to compute some expectation, shown here. But in this case, different from what we've been talking about so far, in this case, let's assume it's hard to sample from pz given z, or it could be the case that samples from pz given z are not very informative. What's an example of the first thing? Well, it's just some distribution z you don't have a way to sample from. Maybe you know how to evaluate the density, but you don't have a process to sample from it. Second thing, simple example with something like this. Imagine you have maybe a Gaussian distribution, very easy to sample from. And then what you want to actually evaluate is the expected value. So this is pz of z. I want to evaluate the expected value maybe of a function that looks like this. So here and here it's non-zero, otherwise it's 0. So this function, f of z over here. So if you're going to just sample from your Gaussian, you're going to get samples that mostly fall over here. The long tail together will also add up to something, same on this side. And very few will actually fall where your expectation has a non-zero contribution. And so most of your samples are wasted. That's exactly what we had over here in our objective. It turned out that the f of z was another probability distribution, but it doesn't really matter, same thing. We have an expectation where we have some f of z, which happens to be a probability distribution, which happen to mostly be 0 if we don't have the right z. And so same issue. So what does importance sampling do? Importance sampling says the expected value when a sample occurring to pz, you can write it as a summation. If you like continuous variables, you can put an integral instead of a summation there. Same math we'll go through. Then you can multiply and divide by the same quantity, q of z. Then we realize, actually, if we regroup, this is now an expectation with respect to the distribution qz. And so what we can do now is actually we can sample from qz rather than from pz and do a sample-based expectation that approximates the original thing we're trying to compute with samples that come from q rather than p. Now, so importance sampling is a way to switch the distribution you sample from and still compute an approximation of the original expectation that in the limit, if you have infinitely many samples, will still be correct. So it's unbiased estimate, just need to sample enough. You might say, well, I need more samples because I'm switching up the distribution. I wanted expectation with respect to p. I'm switching it to q. That's going to be worse samples. Actually, we're going to need less samples. And the reason we're going to need less samples is the second thing over here. The samples from pz are not informative in our case. They all would land in regions where there's just 0 contribution. We don't get much. And so by sampling from q, we get samples that give us information, and it's going to be much more efficient than sampling from the original pz. Okay, so let's see if we can now train our latent variable model. So this is again our original objective over here. The expectation here, we are now approximating with a importance sampling estimate. So we will have sampled z's from the q distribution. We correct for that by dividing by q and multiplying by pz. And then this here is what in the generic importance sampling slide was f of z. That's what we're computing the expectation of, effectively. And so what do we see happen with this ratio? If you sample something that under q is very likely, but under p is not very likely, then you sample something you shouldn't be sampling that much, according to p, you will scale it down, the contribution. And you say, well, what's the use? Well, the use is, of course, again, when this term here is very high, and you can somehow manage to sample in that space, because then together it'll still contribute a lot. And so the name of the game is really about finding some distribution qz that tells us which z's are likely given the xi. And so here we're going to make our z sampler depend on the xi rather than sampling the same z for all of them. Actually, I want to give one additional reference, Edward, for your question earlier. I think the way you've been thinking about it, if you look up transport problems, that's a line of approaches that goes in the direction you're thinking about it, where there might be a one-to-one match in some way. And so there's a bunch of work in that direction if you want to dig deeper. But so we have here this thing. Bayes' rule tells us what it is. So why not sample from this? If we do that, we'll get very informative samples, efficient calculation of our expectation. Turns out, typically, this is not easy to sample from. It's not clear how to sample from this thing. Like, yes, we can sample from PZ. We can then sample this xi given z. That's all easy. But then that doesn't really give us a sample from this posterior. It just gives us a sample from the original distribution. It has not really conditioned yet on the xi. And so the condition on xi, not clear how to do it, unless it's, again, where you can just sum out over all z's. Because this thing on the bottom here, again, is the complicated term up top that you have to deal with. All right, so we want something like that. That would intuitively be the right z's to sample. How do we get it? Something that's close. So the principle of the variational approach, and I'm saying this in general. This is not about variational autoencoders, just generally variational approaches is we can't directly use the P that we want to use for some reason. In this case, what's the P we want to use? It's this thing over here. That's what we want to use. But we can't sample from it. So what can we do? We can instead propose a parameterized distribution Q that we know we can work with easily. So we're going to take some kind of Q that's easy to work with. Maybe it's a Gaussian distribution, something easy to work with. In this case, easy to sample from. That's what we care about. And then we're going to try to find a parameter setting, so setting for the mu and the sigma, that makes it as good as possible. So we're going to try to find a Gaussian distribution that's as close as possible to the actual posterior of z given xi. Once we have found a Gaussian distribution that's close, we can sample from that and use it in our importance sampling. Now I might ask the question, does it matter that my Q is only close and is not the actual posterior? Well, actually, importance sampling is valid with every Q. It's not making the importance sampling invalid to not have exactly the posterior you want. It's still a valid importance sampling scheme. We know it's probably going to be a more efficient scheme if we can sample from closer to the exact posterior than when we sample from far away. So we do want to get as close as possible. There's nothing invalid about sampling something that's just approximate to the posterior that we want to sample from. Okay, so how do we get close to this thing? Find a Gaussian that's close to this. Well, here's what's typically done in these variational kind of derivations. You want to find some kind of Q. You want it to be close to some other distribution. In this case, P, parentheses missing. P theta z given xi. Well, what does KL do? It measures distance between two. If we can somehow find a Q that's close to this, we're all set. You might say, how's that even possible? If we can't work with P theta, how are we going to find a Q that's going to make this 0? Actually, we're not going to find a Q that makes this 0. Because our Q is going to be just a Gaussian. The actual posterior is not likely going to be a Gaussian. It's going to be something else. But hopefully we find something that's close by solving this optimization problem. And once we found something that's close by solving this optimization, we can use it. So what is the KL? It's the expected value under the first distribution of the log odds of the two distributions. Then the P theta is actually not given to us, right? The model is z to x. And we have a P theta x given z, but we don't have a P theta z given x. In fact, that's the thing we don't know how to get. That's the whole reason we're doing this. But we know how to write out Bayes' rule. Bayes' rule says that's Px given z, Pz divided by P of x. The log of a product is the sum of the logs. If it's a division, it's a subtraction. And so we can write this out all separate terms. And actually, this one here does not depend on z, so it can be moved off to the side. So we have a minimization here of an objective and then some constant independent of z, so this is the part that matters. If we can run an optimization on this, if Q is going to be a Gaussian, find a mean and a variance that make this as small as possible. So haven't told you yet how to optimize this. We'll see that in a moment. But at least we have an objective now. And we'll do some kind of stochastic gradient descent because it's an expectation with respect to a distribution that we control. So we know how to sample from Q by design. So we can sample from it, do some SGD, optimize this objective. Why do we know we can do this? We can sample from this, so no problem. We can evaluate this because we chose it to be in a family that's easy to evaluate. This one, Pz given Z, we also chose to be easy to work with. And then P theta xi given Z, typically a big neural network going from Z to X. But again, it's a network that we can run through. We might not have the perfect theta yet, but for every theta we have, we can run through it and evaluate this. So all the terms in the objective are easy to work with. We just need to run an optimization. So now, usually, it wouldn't be done this way. And people would take one more step. So what we do here is, if we were to go back to our original objective, we want to train. To train, we have an important sampled version of that objective. Each term requires us to find a Q for that xi. But if you think about it, finding that Q is in some sense learning a mapping. A mapping from, if I'm given X, what might be the Z? If I'm given an image, can I count how many dogs, how many benches, and so forth? Maybe that's what's happening under the hood. A neural network should be pretty good at this. So instead of trying to solve this optimization for each image separately, you should be able to do something called amortized inference, where you solve the same problem. If you solve the same problem many, many times, instead of solving it separately every time, we take a sum of all the objectives and parameterize our Q. So our Q is now going to be a neural network that turns X into, if it was a Gaussian, a mean and a variance. This is faster. It regularizes because the way you go from X to Z is now through a network that is some smooth structure to it. And then downside, not as precise because you're making two approximations now. The first approximation is you wanted P of Z given X. You said, uh-oh, I'm going to take a function class I can work with, let's say Gaussians. Then we do another step. We say, actually, the Gaussian is going to be parameterized where every inference term is going to have to use the same parameterization to output their mean and covariance. So two approximations being made, but that's how people do it because it's actually more efficient that way. You don't have to run the optimization from scratch for every new xi because your neural network will have learned how to predict a reasonable zi from all the other examples in the past. So amortized inference, we have a min of a sum of KLs. So we want to find multiple posteriors, Z given X, approximate posteriors going in here. The way it's often drawn is this way. Our original network has the solid arrow. We have Z, go from Z to X. That's where we have our network set up for. And then the dashed notation means that it's not part of our generative model, but it's part of our inference model. We're going to learn a network that goes the other way to help us do inference. Q phi Z given X could be Gaussian. So what would this look like? It makes it a little more concrete. You might have some X, which might be some image. It would get processed through a bunch of convolutional layers maybe some self-attention layers, maybe some other layers, whatever structure you want. At some point, after a bunch of processing, it'll output a mu and a sigma. More likely, it'll output the log of sigma just because that's easier to work with, but it'll output mu and a sigma. That tells you the distribution. This is telling you Z according to Q Z given X, which is going to be a normal of over Z with a mean that phi, the parameters play a role that turn X into mu and that turn X into sigma. So that's a concrete incarnation underneath. If you now want to sample, all you have to do is you sample epsilon from a unit normal, and you say Z equals mu plus epsilon times sigma. And so this way we can sample, and we can go back to our objective and maximize an approximation of the log likelihood of our data. Let me pause here for a moment, because this kind of covers all the foundations that we're going to need for everything else. Yes? Is amortized inference parameter sharing? That's one way to think of it. I wouldn't use the word parameter sharing per se, because I would say we're going from, in some sense, a non-parameterized or barely parameterized distribution QZ for each of them that just directly outputs a mean and a variance and doesn't worry about any neural network parameters. So I guess here, in some sense, there's a mu I and a sigma I for all I. And then here, there's just a phi, which will turn, of course, the neural network, the phi will turn the xi into a mu I and a sigma I. So in that sense, I mean, it's a way of parameter sharing, but it's not just that you had many networks, you turn it into one. It's just that you had, these things just would fall out of an optimization. There's no network involved. It's just an optimization, and you find a mu and a sigma. And you can always do that. And you'd be actually more precise in getting closer to the posterior, but you have to do a full optimization for each example. And so it's a little less about parameter sharing than about sharing the computation. Once you've found a good inference network Q phi, you can, even without any optimization, already use it on a new xi. You could say, I've learned a pretty decent Q phi. Let me just use it now in my importance sampling without having to rerun an optimization every time. Other questions? So the importance weighted autoencoder then effectively just comes down to this. What was our objective? Log likelihood. We approximated the probability of a data sample xi with a importance sampled, so samples coming from this importance sampling proposal distribution, empirical expectation, compensating for the fact that we're sampling from Q rather than Z. But of course, that makes us find good Z's to make this last term one that is not always zero or zero gradients. And we had to make sure that our Q phi is close to the posterior to make that actually true, that you have interesting samples. The importance weighted autoencoder essentially does this, but then instead of saying I have these two optimizations, which is one way to think of it, you can also think of it as like, actually, this is term 1, this is term 2, and I'm going to maximize term 1 minus term 2. Minus term 2 because there's a minimization here. And so you maximize over theta and phi the subtraction of those two terms. So you have one optimization, but actually once you take gradients, the thetas will only participate here and so forth. But yeah, that's the general setup. It's actually, what we covered here is slightly more advanced than the regular variational autoencoder in some way. This is an improvement to it. The regular variational autoencoder, which we'll see soon, essentially uses only one sample here instead of a summation over multiple samples. But it has a slightly less intuitive derivation, I would say. The derivation is more magical, whereas what we covered so far, I would say is it's a long but very first principle, step-by-step solving the problems we have to get to the solution we now have. So there are some interesting things you can prove about the IWAE. That is, if you have the real objective is always larger than the objective you get in this importance weighted formulation. That's always nice. When you're maximizing, you'd like to be maximizing something that's bounded by the real thing, so you don't have an opportunity to find some maximum that goes way above what you could get. And so there's some kind of real optimization landscape, and then you know that what you're doing actually working with something maybe like this. That's nice. You don't want it to be not bounded in something that shoots right through, but maybe it would shoot right through here and you're not happy. Another property is that if you use more terms inside the importance sampling, you will do better on expectation. I mean, you can have a good sample, a bad sample, but on expectation, you will do better when you have more terms. In the limit, and we know that because we know it's an exact expectation. No matter what Q we sample from, if we have infinitely many samples, we will have the exact expectation and we'll have the original objective. So we have a whole gradual progression from one sample will turn out to be the regular VAE to many samples, going more and more and more precise. Of course, more cost. And so it's not always clear that you want to pay the price for more samples to do all the calculation for more samples, but it does make you more precise for a given number of data points that you consider in your objective. Yes?
What's the L?
Oh, the L is the likelihood. Good point. So L is this thing. Well, actually, it's this thing. And then the K refers to, well, really capital K would be our capital K here, but in the paper, they call it small k. So yeah, this is directly taken from the paper. And they call Z H for some reason. Yeah. Let's call it Z. Let's call it Z. There we go. Yes?
Sorry, in the previous slide, when you need to sample from the choosing, how can you optimize the two terms together?
Say it again?
Because you need to sample from the Q TKI, right?
Yeah, so you're asking about the optimization. We'll actually look at optimization soon. So let me skip 2 slides ahead here to look at the outline. You're essentially skipping to there. So we'll get to that. We're just not there just yet. Yes?
So on the slide you were just previously on, we're minimizing the KL between Q of Z given X and P of Z given X.
Correct.
How do we know that P of Z given X will always be the best distribution that we want our Q to match?
Well, that's a good question. I don't know if it's guaranteed to be the best. It might or might not be guaranteed. I mean, I'm saying there could be a result out there that says that this is guaranteed to be the best. There might not be such a result out there. I don't know the answer. That's all I'm saying. I'm not saying it's an open problem. It could be an open problem, maybe not. But we know it's a pretty good one because essentially if you think about the kind of data we're trying to model and the kind of structure we're trying to recover, we're trying to recover structure where the latent variables Z are such that for a given X, there ideally is only one latent variable Z that's a good explanation for it. And that would be an explanation for that X in a compact way. And so if we assume that for each X there's going to be only one latent variable that's a good thing, then you need to sample that specific Z to get anything to contribute in this optimization. And so that Z is going to be the posterior. Now, that's my reasoning here is starting from the point we're going to try to find latent variable models where the Z and the X have a nice correspondence. In principle, there could be latent variable models where for every X you want to have many, many Z's that could explain it. And then, I don't know how well it's going to work out. You might not be able to get away with a Gaussian because we think only one explanation is good, a Gaussian makes some sense because you can peak your Gaussian around that one point. But if you want to build a model where there's many explanations for a single X, then maybe a Gaussian is not that great because now you need something multimodal under the hood. And so it wouldn't be changing necessarily that we want this objective to be optimized, but we might change the structure we have for QZ given X. And so people look at this also. They might say, okay, what should be my neural network for Q phi? Should it just output a Gaussian or something more complex than just a Gaussian? Could it be an autoregressive model, a flow model? There's all kinds of things people put in there to make it more complex, potentially capture more intricate latent structure. At the same time, if you think your latent structure should be a simple way of explaining your data, maybe you don't want to put that into your architecture. You don't want your Q phi to be able to represent something very complicated because then you're not recovering simple disentangled aspects of your data. So there's a proof here for that theorem. Not going to step through it, but this, just so you know, the theorem on this slide has an actual proof that you can work through that shows that indeed the more samples you have on the inside, the more precise you're going to be. And it's a trick with Jensen's inequality, which we'll see something with very soon. Okay, so we've seen now effectively the VAE as an importance-weighted autoencoder. If we just were to use one importance sample, it would match up. But there's another derivation, and I want to show you the other derivation because that's what you'll often see. And there's actually 2 other derivations. So I want to show you 2 other derivations that you'll often see, and so they are familiar to you, and sometimes they're more convenient to work with. So I should derive this live, but from some notes. So what we're going to do is I'm going to again maximize over theta, sum over I log p theta xi, which we know is max over theta, sum over I log sum over z, pzz times p theta xi given z. So that's just our definition so far. We haven't changed anything yet. Then we're going to play the same trick we play in importance sampling, which is multiply and divide by the same quantity. So QZ, QZ. That's going to be a 1 multiplied in PZ, P theta, XI given Z. Now, in importance sampling, we kept with this. What we're going to do now is going to say, well, a log of a sum is not that convenient. Log of a sum of a product, but if I can somehow swap this summation and this log, that would be nice, because then I have a sum of a log of a product, and the sum of a log of a product is a sum of the logs, and things simplify. I have all these separate simpler terms, not this gigantic thing together. So can we swap? Well, Chen's inequality. So Chen's inequality says that always have to redraw it. So it says that the log of the expected value of some quantity, log of expected value of some quantity, let's say just the variable z for now. We're going to compare it with expected value of the log of z and try to think which one is larger. So z over here, z1, z2, log of z2, log of z1. Then the log of the expected value, if we have half z1, z2, then the log of the expected value is going to be up here. And the expected value of the log is going to be the line between these and over here. So expected value of the log is smaller. This is what we have. Log of expected value bigger than expected value of the log. Okay, so let's put that in here. Max over theta, sum over I. And then our expected value comes out. So expected value z according to qz of log, and then pzz, qz, p theta, xi given z, which is equal to max over theta, sum over I, expected value z according to qz, log pzz, plus expected value z qz, log p theta xi given z minus expected value z according to qz, log qz. So what we've done here is always true. For any qz, we can do this. There's something interesting about Jensen's inequality that says that if, maybe let's call this x somehow, which might depend on z, x, which might depend on z. If x is a constant, then this holds with equality. So if the thing is a constant, what has to be a constant? This thing over here. If this is equal to a constant, then equality. We know the left side, oh, I forgot to put the smaller than or equal. So here it's equal, but there was a thing here. We know it's always smaller than or equal. We know it can be made equal if we make this a constant. What does it mean to make this a constant? Well, Q is something we can choose. It's our variational distribution. It's the distribution we introduced to play with. Well, if we make Q z proportional to p z z p theta xi given z, then we have equality. Can we do that? This distribution over z, well, x is fixed, so this is an unnormalized distribution over z. What really is on the other side here is p theta z given xi once you normalize it. So what it's saying is that that same thing that we wanted as our importance sampling distribution, also when applying Jensen's inequality, is a thing we actually wish we have inside Q. We might or might not have it exactly, but we actually do know that we can replace this thing here with an equality if we also insert a max over Q. Because then Q will take on that exact posterior value, and this will be an equality. If we don't achieve the max, if we just have AQ, then it's going to be potentially smaller. So that's really nice. We now have an objective here. We will actually maximize over theta and over Q, because it's good to make this as high as possible, get an equality in that bound, because we're trying to get as high as possible. We maximize over both theta and Q. This objective here, this thing is called variational lower bound, VLB, variational lower bound, sometimes called elbow for evidence, lower bound. And so we ended up with effectively the same objective we had with importance weighted approach to this. We're trying to find the same Q, it turns out. In this case, as we try to find the Q, it can all be seen as part of one objective, which is nice. We just have this one objective, and within that objective, as long as we maximize it over choices of Q, we will get as close as possible and ultimately reach equality. And so we can optimize Q, then theta, then Q, then theta, or both at the same time to find a good theta here that models our data. I propose we take a break here, and we'll resume with this and a new derivation of it after the break. So let's take a break till 6:35. All right, let's restart. So before the break, we kind of covered a lot. Maybe let's step through the outline. We saw some motivation for why latent variable models might be things we want to learn. We looked at an exact objective, but we saw that, well, if our latent space has a large number of values the Z can take on, it's not going to be practical to work with. Then we said, well, we can just sample the Z, but if we sample from the prior, since typically a given xi only has one Z or a very small number of Z that match up well with it, if we just sample from the prior, we're not getting anything useful. So we're going to do importance sampling and sample from the posterior of Z given x, which actually we can't do exactly, but we can use a variational approximation to get close to it. We then saw that from that we got an objective we can actually train. We can train both the parameters phi of the variational distribution q phi that goes from x to z, and the parameters theta of the distribution goes from z to x p theta. Then we actually saw a new derivation of the same thing via Jensen's inequality. We said we want to maximize this expectation. We make the log of the expectation to the expectation of the log, and we can do that. And if what's behind the log is a constant, then this holds with equality. Otherwise, we make it smaller, but we want to make it as large as possible. So we're going to try to make it hold with equality. So we get to maximize over q and over theta when we do this. This is one derivation. Here's another derivation. Think again about this KL we've been interested in. We can write it out. It's an expectation of the log of the first distribution minus log of the second distribution. we can then, what is a conditional? What is this joint? And ultimately what we get, this thing does not depend on z, so we bring it out. We get an expression where we have the KL between the variational distribution x, qx of z, and the posterior z given x is equal to, the thing here is actually our variational lower bound, is the same expression. Now, the way to think of it is that we can actually change this to the other side, and then we see that log p of x, log p of x equals this thing over here. This here is our variational lower bound. This thing is always bigger than 0. It's a KL divergence. They're always bigger than 0. So we see that log p of x is bigger than or equal to our variational lower bound, and the gap is the KL. It's effectively the same result again, but now it's quantified. In the previous derivation, we knew if we made Q equal to the posterior, it would hold with equality. But if we did not make it equal, we did not know how much we lost, how far we were off. With this derivation here, it also tells us how far we're off. The KL between Q and PZ given X is how far we're off from having equality. So also another way to show that if they are equal, then the bound holds with equality, and we have the exact log probability. So we've now derived effectively the same objective 3 times. Once through importance sampling, which was a little more sophisticated in some sense. We had multiple terms in there, which can be more precise. Then via Jensen's inequality and this derivation here starting from the KL. Okay, that means at this point we actually have something we can try to optimize. So we wanted to optimize log probability of the data. We have a variational lower bound and something else. We can optimize our variational lower bound with some stochastic gradient descent. We'll see more details later to optimize the objective we actually care about approximately, which is this one over here. From Jensen's inequality, we also know that the optimal qxz of the variational lower bound is pz given x. So in the optimization, this thing over here, we don't need to work with the second term. We know that the first set of terms is enough. When we fully optimize that over q and theta, we actually make that second term close to 0 automatically. This is a good thing, by the way, because this thing here directly is not that easy to work with. So we just have to deal with the first part. All right, so what do we do then? We have our variational lower bound, which is this thing over here. We have an expectation over the data. Each data instance x will have a term that looks like this, and it'll be a lower bound on the real objective. We try to make this as high as possible, which will drive this up also. So how do we optimize this? So far, as we've done optimization, the stochasticity in our networks, when we had autoaggressive models, was happening in some sense at the end. The softmax at the end was the stochasticity. And so it makes it a little different from what we're doing here. Here, we're somehow optimizing something where the expectation is over q, z according to q, and we're optimizing over q. So the distribution that we're optimizing over sits inside the thing that we're sampling from. And so that's a little different from the optimizations we've done in previous lectures. So we need to do a little bit of kind of background on how to optimize these kinds of expectations, and then we'll apply it to the variational lower bound and elbow. So there's 2 ways to do this. So 2 ways of computing these gradients. And the first one is super general, likelihood ratio gradients. Can always work, but it's high variance. So whenever you can do the other one, you'll probably prefer it. But the other one's not always usable. So let's start with the general one, likelihood ratio gradient. So we're really talking about something where we have an expected value z according to some distribution qz of some function f of z. And this qz is parameterized by some phi. And we're trying to, let's say, maximize over phi this thing over here. If you just do the very naive thing, you just say, hey, I know this is an expectation. I'm just going to draw some samples, and I have some, z from q phi z, zi, and then I say, okay, now I have an empirical expectation. I have, sum 1 over k, I equal 1 through k, and then f of zi. That's my empirical expectation. But your phi has disappeared. So in the past lectures, we could always take this expectation, make it empirical, and the parameters were not disappearing. But the problem here is the parameters live over here in the thing that we use to sample. So we can't just go ahead and sample and then say, now let's take the gradient of this thing with respect to phi. It's too late. It's gone. It's the z's that showed up are really coming from your choice of phi, and it's now too late. In fact, it would be wrong to do it at this point, because you do it at this point, you say, oh, gradient is 0. But that's not true at all. You change your distribution q, the expectation is going to definitely change for most f of z. So let's go back to more basic principles. Max over phi. Let's write this expectation explicitly. Sum or integral. I'm going to write a sum, but integral is all the same. Sum q phi of z, f of z. Now my phi is not gone yet. Then I want to do the max. I want to take a gradient. So gradient with respect to phi of this thing over here is equal to sum over z grad phi q phi of z times f of z. Now, typically what's done from here is, okay, well, again, let's assume as many z's are possible. So I can't exactly do the summation. If I can do exactly the summation, we're done. We just do the summation, we're good to go. We cannot do the summation exactly. I want to make a sample approximation, but this is not an expectation. This is a summation, but not an expectation. Let's make it into an expectation so we can have a sample approximation. So making an expectation, sum over z, q phi z, divided by q phi z, q grad q phi z, f of z. This is the expected value z according to q phi z of grad phi q phi z over q phi z times f of z. We should also write as expected value z q phi z times grad with respect to phi log q phi z times f of z. This thing is an expectation, so I can approximate it by samples from q phi. It's going to be 1 over k, sum I equal 1 through k, grad phi log q phi zi times f of zi. This is now a gradient, and the expected value of this is, if I take the expectation of that thing, I get this thing, which is the exact thing. So I have an expression. If I take the expectation of it, it's exact, which also means if I take infinitely many samples, well, it's continuous, I mean a very large infinite, but if you have a very large infinite number of samples, you will have the exact gradient. So we're good to go. And then we take a small number of samples in practice and take a step and repeat. Now, intuitively, what's happening here, if we look at this, it's saying that I'm going to sample my z's, a bunch of z's. I'm going to evaluate for each z I sampled f of z. And if f of z is a large positive number, I'm going to make the log probability of that z being sampled again higher. Because I'm increasing the log probability for anything I sampled that's multiplied with a positive number. If f of zi is negative, then I'm trying to decrease the log probability of the thing I just sampled. Turns out it's a little more subtle than that, in that maybe all your FZs are positive, in which case, because the distribution has to normalize, the more positive ones will be pushed up in probability with an update, and the not so positive ones will be likely pushed down a little bit to keep things normalized. That'll happen automatically for you. So people who've done reinforcement learning, of course, recognize this. Usually, that's the reinforced policy gradient, and they also know that, in fact, you can subtract out a constant to center this. So you can say, if I have a bunch of samples, I can subtract out the average. What's the average f of c I tend to get? And then the grad log probability will be multiplied with f minus the average. What's above average will be pushed up. What's below average will be pushed down explicitly. We can look at this for a Gaussian. Imagine here we're trying to fit a Gaussian, so we're trying to optimize this expectation over here. So what that means is we want the Gaussian to be over here. But initially, our Gaussian is centered at 0 and looks like roughly unit variance. So we start with a Gaussian. Our phi, in this case, is mu of the Gaussian, because we're not changing I. So our q phi is equal to a normal distribution of z, normal distribution over z, with, or let's call it z here, with mean phi and fixed covariance sigma squared. Or actually, it's even 1, so just fixed. To unit variance. So we all know what we want. We want to find phi that's equal 5, 5. That's where it needs to be. We can read off the solution. But the question is, what's happening when we run gradient descent on this problem? Is it going to move in the right direction? Well, let's take a look at this equation again. So we have, for each sample, we look at a contribution of grad phi log q phi ci times f of ci. For a Gaussian, what is this thing over here? This thing's going to be, Gaussian has something up front that has the variance in it, but we're not optimizing over the variance, so that's not going to have a derivative. That's non-zero, so the only thing that matters is going to be what's in the exponent. Is going to be minus 1/2 distance between z and that 5 point squared. I'm going to have grad respect to phi. Hold on, it's a probability. I didn't put a probability there. So erase that for a moment. So q phi of zi is going to be 1 over 2 pi to the 1, well, two-dimensional, so 2 over 2, then determinant of the identity matrix, which is 1 to the 1/2, then e to the negative 1/2 z minus mu, well, we call mu phi squared. That's our probability density here. Then what we have for, let's erase a few things. Give ourselves some space. This means that log q phi ci equal minus log 2 pi minus 1/2 z minus phi. Well, technically the norm, but let's think about it as 1d z minus phi squared. Then we have grad respect to phi. This will not have anything. So 0 here, and this will be, well, really there's a z minus phi identity. Transpose here is z minus phi. So it's going to be minus 1/2 z minus phi. And then just need to check the sign. This is the correct sign. I think it's the correct sign. So this is what we end up with. So we see is that this grad is essentially saying, I'm looking at z and phi. I'm going to take a step in the direction of my current z away from my current phi. So let's say I sampled this z. This is my phi, which is right in the middle there. Maybe blue is not the best color for this. Let's see. Green. My phi is right there. I'm going to take a step in the direction of z, and make phi move in the direction of z, but how far? Proportional to f of z. So if this was a good z, I'm going to step very much in that direction. If it's not so good a z, step less in that direction. So all of these z's here, well, some are a little better, some a little worse, but essentially you're kind of just trying to move to all of them, a little more to the ones that are in this direction than the ones that are in this direction. This is going to be pretty noisy. And so if you only sample two z's, you sample one over here, you'll essentially move roughly this way, and that's it. That's what happens. So we have some motion of this thing, but it hops all over the place, and doesn't really have a really good zoning in on the target. Again, if you take infinitely many samples, no problem, you'll get the perfect gradient. But with a finite number of samples, it's not going to zone in on the target all that well. So what else can we do? The reparameterization trick. Yes, Edward.
I think in our case, f of z actually includes q of v of v. So wouldn't we have like a square term that you have to account for?
So the question is, how will this apply in our case? And that's coming later. So yeah, I'm saying the question you're asking comes on a later slide. So another thing we can do is to say, well, we had this thing we're trying to optimize. Let's go back to what we were trying to do when we started out. We're trying to optimize this thing over here, okay? And we did it in a very generic way. But a Gaussian is not that generic. We can look under the hood maybe and do better by looking under the hood. So trying to optimize expected value z according to q phi z of f of z, where q phi of z is equal to normal mu, let's say, sigma squared. Well, that means z equals mu plus epsilon times sigma, with epsilon coming from normal 0, 1. So we can rewrite, and this is the reparameterization of the reparameterization trick. This is the reparameterization right here. We can write as expected value epsilon from a normal 0, 1 of f of mu plus epsilon sigma. And so the thing we were worried about at first, which is if we just draw some samples and then look at the expectation, we've lost the fact that these samples had a parameter mu in it, parameter phi in it. So here, when we, if we just did our sampling, the phi had already been used and wasn't present anymore. Well, by now, having an expectation with respect to something that does not have phi in it, no phi here, we can actually go back to the standard kind of thing we do. We have an expectation, we approximate it with some samples, sum over I, 1 over k, I from 1 through k, f of mu, actually mu is fixed, mu plus epsilon I times sigma. And now we can take the gradient of this thing with respect to mu and sigma to optimize. And so we simplified our life a lot. Now what we did here requires that you can reparameterize your distribution. Now in principle, we actually know you can in principle always do this. I mean, in principle, you can set up at least for continuous variables, you can in principle set up a flow. And we know flows are general. And you could sample from your z in the flow, and then, you have a reparameterization that allows you to sample from a simple distribution and then you pushed all the parameters inside the z instead of having it in the sampling process over here. Now, if you're going to have a massive flow, maybe it's not that efficient to work with. But for things like a Gaussian, it's very convenient. You can always do it very easily. If you have discrete distributions, it's harder. It's not so clear what to do. If you have a discrete distribution, you cannot apply the same trick. And so typically when you have continuous variables, you'll apply this trick. You have a discrete distribution, you do a likelihood ratio, or sometimes you think through, do I really need a discrete distribution? Can I not swap it by a continuous variable? Instead of 0, 1, what about uniform between 0 and 1? And maybe I regularize it to help it go to 0 or 1 on the extremes, but I don't necessarily have only 0, 1, because then it's harder to deal with. So this is the reparameterization trick. This is going to have much lower variance. If you look at the optimization with this, essentially you get some samples. Then what happens here in your gradient? So let's look at the gradient here. This gradient here, I will have some sample, f of mu plus epsilon I times sigma. The gradient of this, with respect to my parameters, in this case mu, because sigma is kept fixed, is just going to say, well, this thing here is mu plus epsilon I times sigma minus that 5 point. This is literally saying, bring my mu parameter to 5. It's pushing it literally in that direction. It's a little bit of a contribution here, so a little bit of noise from that. It's really pushing it to 5 up to this noise contribution, but mostly it's pushing it in the 5 direction. Compare that with what we had before, where it just said, whatever you sampled, I'm going to push mu in the direction of whatever you sampled. And how much I push in that direction depends on f. Here, the gradient itself tends to be pointed roughly in the right direction every single time. So you run this, here's what you get. Kind of gradually moves towards the target, doesn't hop around like we had before. So 2 ways to do this. The second way clearly works better if you have a Gaussian distribution, is the one you're going to use if you have a Gaussian underneath, anything like that. But the other one can be important because sometimes you want a discrete distribution. Really, that is what matters. And so when you have a discrete distribution, you have the likelihood ratio. And Edward's question was, well, what happens? The f of z is more complex. Let's see what happens. So we have a expected value. Actually, let me switch back to blue. We have an expected value where z will come from q phi z of xi. Our variational distribution that we're learning, q phi, is predicting good z's, or distribution over good z's. Then we have log pzz plus log p theta xi given z plus, minus log q phi z given xi. So before we had just the f of z, but actually here we have a f of z and phi, because phi appears in here. So this is what we're optimizing for, and we're optimizing with respect to both theta and phi. These are, when the sum over i's that I left out here over the data points we have. But so one term in SGD will be just this single term in the objective. Gradient with respect to theta is fairly straightforward. Where does theta appear? It appears over here. That's it. So gradient with respect to theta, using the likelihood ratio method, whatever method you use, you can decide that later, but theta does not appear over here, so we don't have to worry about that. And so we just have an expected value of z according to q phi of log p theta xi given z, gradient of that, and we'll just have this be approximately equal to gradient of depending how many samples you take. Often people only take one, but you could take more. Let's take more. Let's say I or k from 1 through k. Samples zk. We have log p theta xi given zk. Zk coming from q phi of z given xi. So what do? We have our q phi, we sample some z's, and we have an objective here, and we optimize p theta xi given z. This is the network, right? We have z going to x. On here is a p theta x given z. That neural net, we're just directly optimizing here. We're trying to optimize the probability of the output x we're seeing given some latent variable z. So that's just standard backprop taken care of. Then the other one, carry respect to phi, that's a tricky one because we sample with q phi. That's what we did all that work for, the side tour where we looked at likelihood ratio and reparameterization. Let's say we do likelihood ratio. We can definitely do that for the first part, the first two terms, but then, so here, no problem, but then here we have this phi. So we got to keep in mind that we have some more derivatives we have to take. So let's take a look at just the first part. Will just be, we know how it goes, it'll just be grad phi q phi zk times log p c zk plus log p theta xi given zk. And then this one will be here. So that's what we had before, but then there will be an additional term because derivative with respect to this thing. What's that? So we have derivative back there, so we have an expected value with z according to q phi z xi. And then we have of minus grad with respect to phi of log q phi z given xi. So that's an extra term. We cannot ignore that, it seems, but let's take a closer look. Grad of this thing is minus grad with respect to phi z given xi. Grad with respect to phi q phi z given xi. Then over q phi z given xi. And then an expectation on the outside, z according to q phi. Okay, now next thing we do, we say expectation of the grad is grad. Let's see, how do we do that? Actually, these two here, they cancel out. So what we're left with is, so this is going to be, expectation will be sum over all possible z, q phi of z given xi times the grad over q phi z given xi. So these two cancel out. We're just left with the top here, grad q phi z given xi. We bring the grad out. Then we have grad with respect to phi, sum over z, q phi z given xi. This thing is a distribution, sums to 1. Grad with respect to phi of 1 is 0. So we did all this work to deal with this q phi that's hidden in there that we're worried about, to realize the gradient contribution is 0, and we actually don't need to worry about it. But we didn't know it until we did the work, but now we know. So this is all we actually need to optimize with respect to phi. Okay, so we now know how to train a VAE fully. We have this objective here. We can sample from q phi. We can apply the likelihood ratio gradient to get a gradient and repeat. We have a gradient for phi and theta. We're good to go. Here is this kind of set up in slides, the same math. How about pathwise derivative? Let's see. Yeah, I'm not 100% sure how we're doing on time, and we've already done a lot of math. So I'm going to leave this on the slides for you to look at. But essentially, you can do the same thing we did in the simple derivation of pathwise derivative. You replace your appearances of z with an appearance of mu phi of x and sigma phi of x times epsilon. And at that point, it becomes a normal expectation. You don't have an, you can just sample from your unit Gaussian, do stochastic gradient descent, you're good to go. Okay, so often people take only 1 or 2 samples, by the way. And so now, if we look at the full expression, let z be this thing over here now. We have variational lower bound like this. We're essentially going to substitute that z expression into here. And our expectation is going to be over epsilon sampled from a unit normal. This has no phi, no theta, so we can just sample a bunch of epsilons, get a bunch of these terms, and then do a stochastic gradient descent. Okay, we've covered a lot of math. Ultimately, what it comes down to is that we have a latent variable model. Z is what we sample first in the generative model, which can generate x. But we also want to do inference the other way, both to find z from x, to find a latent representation, and because to train p theta x given z, we actually need to recover the correct z's in our underlying model to be able to train efficiently. And so this is an important part of training as well as representation learning. There's a question there? Why is it called pathwise derivative? So I think this comes from controls. So a lot of these things that tricks people play with recurrent neural nets and deep neural nets actually were applied already a long time ago in controls, where you have state at time t, action results in state at time t plus 1, new action, state at time t plus 2, and so forth. It looks a lot like a neural net, it's just that it's a sequence of states and actions rather than a sequence of hidden states. Otherwise, effectively looks the same. And so in that literature, when you think about pathwise derivative, what you're effectively doing is you're saying there is stochasticity in every transition. So as I go from t to t plus 1 to t plus 2, there's stochasticity. I'm going to assume that stochasticity comes from a Gaussian, unit norm Gaussian, and then it's going to get multiplied by a variance and added some mean and so forth as needed. And once you have a rollout that happened, you have a path. Sequence of states and actions, but also the noise that happened along that rollout or that path. You do take a derivative of that. You can freeze the noise. You can say, let's assume the noise is constant. It doesn't change in my next rollout. If I could have a rollout with the exact same noise, how should I change the parameters in my control policy to improve my performance? And effectively what you're doing is you're changing your path directly. And so you're directly optimizing the path followed by that rollout for that given noise. And the same thing here. We're going to be optimizing for a fixed epsilon, for a single sample. Epsilon is going to be fixed, and we're going to be optimizing the thing that's happening inside a neural net with the epsilon fixed. Whereas the likelihood ratio says something different. It says whatever happened, happened. If it was good, let's make it more likely to happen again. If it was not good, let's make it less likely to happen again, which turns out to have a lot less signal in it. So, VAE, this is our model. We know now how to train it. Oh, question here.
So, when you update the VLBC, when do you sample Z? Because when you're updating like theta and phi.
Oh, you're saying what's the algorithm? The algorithm is I have a current Q phi, I have a current Q phi, I have a current P theta. And I have a bunch of x's. So I have this initialization, and I have x1 through some xm. Then I take a subset, random subset, but maybe it was randomly permuted, so I just take the first couple. For the random subset, maybe even just one, let's say we just grab x1, so pure SGD, no mini batches. We just grab the first one, and then we run Q phi, z given x1, which results in a z1. Once we have z1, we can write out our variational lower bound with that z1 and compute a gradient step on that with that z1 in it, and the expectation replaced by using this c1. If you do likelihood ratio, you get one version. If you do reparameterization trick, you get another version. But either way, this z1 will be used. You're able to make an update to both phi and theta, and then you repeat.
Question.
Yes?
So in practice, these are both neural networks that might have different architectures possible.
Absolutely.
How do we balance their training to make sure that one is stronger than the other works?
So we'll get to that. So here's some training of the VAE, original VAE on MNIST. It's compared with something called wake sleep. Before the VAE was introduced, the best algorithm available was wake sleep. It's in the very end of the slides. As you know, for your interest, wake sleep is not that popular these days, but it was the natural one to compare with at that time, and it was consistently outperforming it, hence people switching over to the new approach. What's on the vertical axis here? This thing here, ideally it would be the log likelihood, essentially nats per dim or something like that. But in this case, we don't have the log likelihood. We only have the lower bound, which means that actually our model might be slightly better than what we're seeing there, because all we get to evaluate is a lower bound on how well we're doing. So we're definitely not overclaiming. We're probably underclaiming when reporting the variational lower bound. So if you compare that with a pixel CNN, if you do better with your variational lower bound than the pixel CNN with its actual log likelihood, you know you definitely trained a model that fits your data more closely. If you do a little bit worse, it might just be that you're actually doing just as well, but the lower bound doesn't achieve the same number. The actual likelihood would have achieved the number. Then MNIST generation. So here are some digits generated. Seems to work pretty well. Then you can do things like, I believe the bottom is some kind of, I think this plot has some interpolation going on where you change your latent code, and as you change it, you kind of see different versions emerge. Here's a direct comparison with autoregressive models. So Pixel CNN has negative log likelihood, so lower is better, 81. And then we have, let's see, where is our variational autoencoder? Oh, I think it's a direct comparison with this plot here. So we are, with the VAE, we are somewhere here, whereas the Pixel CNN gets to 81.30, which is a bit better. Why is it called an autoencoder? It's a question you could ask. Because so far we've really looked at it from the perspective of, can we build a generative model? What's autoencoding about it? If you look at the objective we're optimizing, this thing over here, the first thing is effectively a reconstruction loss. We're checking if we sample, if we have an X, and we from that create a Z sample, then we check how likely is the X under that Z. So essentially saying how likely, if I were to then use P theta X given Z to sample my X and reconstruct it, would I get the original one back? So this is a pure reconstruction loss in the front here. So that's doing the autoencoder part. Then in addition, there is regularization here. It's saying that my posterior of Z given X has to be somewhat close to P of Z. Try to bring it close to something simple. So as you know, with autoencoders, you don't want something too rich in your Z, because then you just memorize the data, and this is always want some kind of regularization. This is one way to regularize. If you think about it in terms of your process, in a typical VAE, you'd have X. X gets processed, generates a mu and a sigma that together turn into Z equals mu plus sigma times epsilon. So what's happening is you don't get to choose your Z. It's not deterministic. It becomes perturbed by sigma times epsilon. And then the decoder, P theta X given z has to somehow compensate for that. Has to say, well, my x got encoded, but then it got perturbed, and then I have to decode it. So what that means is that if you have a small perturbation on your z, you want it to also result in a small perturbation on the x you decode, because otherwise you will not do well on this loss. So it means that similar x's should land in close together in z space. And that's a property you like. You might say, well, why wouldn't I then just, spread out all my, put z's everywhere, all over the space, so every x can be very isolated. And when I get perturbed by this epsilon sigma, it doesn't do anything. I'm the only one there. The reason you can't do that is the regularization. Regularization keeps you in. You kind of have to somehow take all your x's, map them into z space, whereas sometimes they all take up a small sphere of their own, and you're somehow going to pack them into that roughly standard deviation, well, maybe 2 standard deviations away from the origin space. You got to all pack them in there and space them out as much as possible while packing them in there. Okay, so we've seen the foundations. Now we're going to kind of hit relatively quickly some variations on them that are, I would say, really, really surprising how well they work. So, VQ-VAE, vector quantized variational autoencoder. This thing, I believe, first came out in 2017, the first paper. And I would argue very few people paid attention to it because people were so excited about GANs. GANs this, GANs that. I mean, we'll see GANs next week. We'll be excited about them next week. But this week, we're not excited about them as much yet. And people kind of mostly ignored the paper as far as I could tell. But then the second paper came out 2 years later, and the results were so good that now, of course, everybody's paying attention to both papers. So what's the VQ-VAE? What is one of the challenges with VAEs? You take your x, you turn it into this z, and you're now in this unit Gaussian space. If you want to generate new samples, you sample from a Gaussian, you generate an x. But you mapped everything into this Gaussian sphere. And you're saying anything in this Gaussian sphere should be an image. But maybe, I don't know, maybe you map some kind of a dog here and cat here. Sure, but your VAE objective says that you got to fill this sphere, kind of. And so if you only have cats and dogs, you're still trying to get things roughly filled up. Even if you don't get them fully filled up because you maybe leave a little bit of space, when you sample, you will still sample anywhere in this sphere. And so you might sample over here and get something in the middle that doesn't look like a real thing. So really what you need, if you truly have different categories, you need more flexibility in the latent space that you're mapping into. If all you have is this Gaussian, this prior being a Gaussian, you might not get the job done because then you cover a lot. You need to cover it all, and that doesn't really work if things are too different. So what can you do instead? They said, let's map into latent codes that are discrete. So CNN processes. I'm going to train that CNN, of course. This is our Q5, by the way. Processing. Turning it into latent codes. This one here is 53. So this one here, 53. What does that mean? Think of it as a one-hot encoding. So after you run a ConvNet over an image, you will get these, at each usually a reduced resolution pixel, you have a bunch of features. For example, you have maybe 32 depth here, 32 features in that pixel spot. What you then do is you look at all those features that appear everywhere in your image, these 32-dimensional feature vectors, and you say, that's my latent space. My latent space is 32-dimensional. 32-dimensional latent space for each pixel spot. How am I going to model a distribution over this space? I could force it to be Gaussian. That would essentially be a standard VAE kind of model. Instead, I say, we're going to model a discrete distribution to it. So we're going to just, in this space over here, which are really all these vectors, if we were in 2D, we're going to pick some centroids. And if you land anywhere that's not on a centroid, you get mapped to the nearest one. So you can think of it as my latent space, PZ, is going to be a mixture of Gaussians, except not a soft mixture of Gaussian kind of model. It's going to be just a bunch of discrete spots you can be at and nowhere else. And so when you land anywhere here, you would get snapped to over there. might say, that's kind of weird. Why would you do this? But the reason you would do this is because once you have that, once your latent space is discrete, you can actually train a pixel CNN on this thing over here. Because you now have, just like pixel CNN, we had 256 values for our pixels. Here you might have a 256 centroids. That gives you exactly the same as a grayscale image with 8 bits. And so you can train a pixel CNN in this space that says if the first latent vector is a 53, then the next one is likely a 55. The next one is likely a 100, and so forth. That's a very rich model. So we talked in the beginning. Later we'll see how to model PZ. Well, our PZZ is super interesting here and also more expensive to train. It's an autoregressive model, pixel CNN. Now you can have a very precise PZZ. You're not kind of landing in random spots. You can embed your data in this latent space in a way that when you get things back out, you're not going to get these weird interpolations that are not meaningful. You only get meaningful things out. At least that's empirically what starts to happen. So that's the gist. How do you train it? This is the objective. What are we looking at here? Log px given z. Okay, what's that? That is our decoder. How well am I decoding x given the z that I sampled? But this is a quantized, this is going to be a quantized z. Then I also want to be the case that when I quantize my z, it has to be close to one of those centers. So each z that you get from x, so x get turned into some z, has to be close to a center. And I have another part that allows us my centers have to be placed close to my z's. So there's going to be some alternating optimization. Something you say, I generate all my z's, and after I generated them, I can optimize my centers to some kind of k-means type procedure to put my centers in positions that my z's are close. So that part should be easy. That's just k-means. You know how to do that. How about actually optimizing the whole network? Something called straight-through estimator. It's some kind of weird gradient trick, but that's why these stop gradients are showing up here. So that's how you would write it in code. What it essentially means is the following. As you have your 53 here, and you decode, that 53 is turned into the center. So you have some kind of thing here. You turn it into 53, which is a vector that's a discretized version. That's a center instead of the original. So this is ZE of x gets turned into the quantized version of it, which has index 53. The quantized version is then turned into x. When I do backpropagation, the first part is all the same. Nothing changed there. How do I deal with the fact that I quantized here? Just ignore it. It's like you can essentially do the following. You can think of zq of x equals ze of x plus epsilon, which is some noise. That noise is just computed in a very funny way. It's not a Gaussian noise. It's just how far you are from your cluster center, and that's going to be your epsilon. Once you look at it that way, it's just like reparameterization trick. You just, in the path forward, there's some epsilon that gets applied to you, and you assume that epsilon stays the same, and then you can backpropagate all the way through. All right, so experiments. These are some pictures generated with VQVAE. These are actually very promising results even at the time. The VAE with a Gaussian, if you had, let's see, are these reconstructions? Yeah, reconstructions. Back then, reconstructions with a Gaussian latent space would be very smoothed out, not very sharp. It's still a little bit smoothed out, but a lot less. Why? Because this is inherent discrete structure underneath that allows it to essentially snap on to the correct things. It's still not perfect, by no means perfect. Here are some generations. And so, kind of works okay. One thing I should remark actually, the PZ given Z, they train after the fact. The pixel CNN part here gets trained after the fact. So you first just train the encoder, the decoder, and the centers. Once you're done with that, you start training your pixel CNN in that latent space. Question there?
So the algorithm is still called a VAE, so I was curious where the VLB or the evidence lower bound shows up. If it's hidden within the loss function that you showed us.
Let's see. The evidence lower bound is showing up. This is the reconstruction part, and I believe, well, which one of these two is the encoding? I believe this one is the encoding, and then this one is about learning the prior effectively. Yeah, I think that's, I'm not going to claim this 100% certainty, but my sense is this is the decoder, this is the encoder. And now the other part that we don't have showing up as explicitly here is the prior, but it's just kind of a very specific distribution where the prior is being learned with this term over here. Not the complete prior, but the vector quantization part of the prior. So yeah, I think it's all three terms actually. Now, to get realistic, even more realistic, higher resolution images, what they said is, can we take this to the next level? They said, can we take an image, encode, principle, you can reconstruct from that, but then encode again to an even lower resolution, vector quantize, from that decode the mid-level, or what they call bottom level, and get the mid-level vector quantized version here, and together get a decoder to output the image. So what's the difference here? Essentially two things. One is there's a hierarchical latent space now. You first go to bottom level latent space, then top level. Second thing is that top level actually uses self-attention, because at top level the resolution is low enough that you can use self-attention over the entire low resolution image. And bottom level, you use a standard pixel CNN when you learn the prior. So those are the differences. But other than that, it's very similar to the original VQVAE, and the results are really, really good. So here are some images, class conditional random samples. I think this is some ImageNet classes, and looks very realistic. Here is a comparison with Big GAN, Big GAN Deep. So notice the original Big GAN Deep. It's a deeper version of Big GAN. So let's take a look. This is, I believe, some kind of fish category. Definitely there's a lot of fish. But if you look on the right, what you see is that it's always some guy, it seems. I guess fishing in these images is always guys. Like a guy holding a fish, whereas here sometimes it's just a fish, sometimes somebody holding the fish, sometimes it's just somebody who might be on a lake fishing. And so you might look at this and say, well, which one's better? Well, you need to look at your training data to know what's better. And actually in the training data, you will see that there is quite a bit of variation, like shown on the left. And so GAN zoned in on one mode of realistic images, but ignored other modes. Same thing happened for another class here. This is goldfish. On the right, Big GAN captures less modes than VQVAE, which is on the left. And even more extreme here. On the right, you pretty much get all these kind of zoomed out shots of ostrich, I think. And then on the left, you get quite a mix. Some are zoomed out, some are zoomed in, very zoomed in, and so you get better coverage. Of course, people try to avoid GAN mode collapse and so forth, but these are the results with Big GAN D, which is one of the best GAN models at the time. Yes?
You mentioned how you have a two-level hierarchy. Have people tried expanding it?
Maybe people have tried. I've not seen it in a paper where somebody shows it with results that would catch people's attention. I mean, it's probably possible there is a paper out there and the results are not interesting, nobody's seen it. I don't think there's a paper out there where it's very successful and hence everybody would have seen it. In principle, it seems like you should be able to go further. Either more level hierarchy for images, or you can start thinking about videos, where you want temporal hierarchy maybe to get long-term video generation, which would be very interesting too. So you might wonder, how come the VQ-VAE has such good coverage? Is that a fluke? Is that built in? It's actually built in. When you have a likelihood model, let me see if I have a somewhat empty slide here. When you have a likelihood model, sum over I, log probability xi, if anything has very bad likelihood, is going to incur a lot of loss, and you're going to pay most attention to the thing that has very low likelihood. So look at this log probability. Log looks like this, goes to negative infinity here, and then goes up pretty slowly. Like log goes up really, really slowly. So as you go further out, examples that already score pretty well, they can't contribute much anymore. You're already doing well. It's very, very little you can get extra by improving your model for things that already have relatively high likelihood. But anything has a bad likelihood, something here, derivative is very steep. And so when you take your gradient, you're going to be paying attention to anything that has the worst likelihood and crank it up. So that's why with likelihood models, you are essentially pretty much guaranteed to cover all the modes. Because any mode you don't cover, that's bad. I mean, sometimes good, sometimes it's bad. I mean, if you try to fit a distribution that looks like this, it's really a mixture of two Gaussians with a likelihood model of one Gaussian, then you're going to have something that needs to cover both. If you had a different kind of model and you had one Gaussian, you might decide to just go here. And you might like that better. That would be a different optimization you're doing, different result. But with likelihood models, you've got to cover it all, or whatever you don't cover, it's going to contribute so much you start covering it. Okay, what else do we have? So state of the art is the VQ-VAE in terms of quality of image generation for VAEs, and I would say matches up well with GANs and has better coverage. Somebody asked, well, how about those architectures? Encoder, decoder, how complex can we make them? What can we do with them? You could say, what if I have a decoder that is effectively a pixel CNN? So I'd make a latent code, and I condition on the latent code, and then run a full pixel CNN. Of course, sampling would be expensive again. It would kind of defeat a lot of the things that we were trying to do here. Turns out the story is even worse if you do that. So far, all models use a simple distribution for x given z. And since x given z is simple, if x given z is, let's say, deterministic or only a little bit of noise at the individual pixels on the end, but no structured noise anywhere throughout, then all the structure has to come from z. So all the entropy lives in z. So z needs to capture a lot of information, which is good because you have an interesting latent code, but also it's hard to put that all in that latent space. It's sometimes nice when, like in a pixel CNN, you can have, once you generated your pixel next to you, have it influence what you are going to be, because that's a local correlation that's easier to capture at the very end there than to capture in a z that might be many, many layers earlier. So why not put in a powerful decoder? Let's say a full pixel CNN. So we've already done a lot of math, but let me just tell you the conclusion of the math here. The conclusion of the math here is that if you have a very powerful decoder, extremely powerful, that has stochasticity on its own, like a pixel CNN that can introduce stochasticity at the very end, it turns out, because in your variational lower bound, what happens in your variational lower bound? Why is it not exact? Is the KL between QZ and the PZ? Like, so the KL in the middle there. How do you drive this down? Actually, very simple. You drive it down by making your posterior of z given x trivial. If you make pz given x a constant, then your qz can nail it and will not lose anything in the lower bound. Then you use your pixel CNN to get very high likelihood, which is just a pixel CNN ignoring everything that came before it. And so now your lower bound has become exact because you nailed it in the middle, and your pixel CNN takes care of everything else. So if you have a big enough pixel CNN as a decoder, that's what's going to happen. People notice this. Make their decoder more and more powerful, start seeing less and less interesting codes, good likelihoods, but not good codes. So people played tricks, like maybe some kind of penalty to ensure that doesn't happen. But ignoring latent code was kind of noticed by many people. So they say, how about we weaken the models? Maybe add some dropout in autoaggressive conditioning. Maybe a limited receptive field. This is the VAE, which Pieter Chen did a couple years ago. And then doing something with a bit rate, you need to at least have a certain bit rate in the latent variable, otherwise it's not a good distribution. So regularize to something higher entropy explicitly to hopefully then, once you're forced to have entropy, you might as well use it. What does this one do over here? It's essentially a pixel CNN decoder, but it's only at the very end and only has local access. So pixel CNN receptive field, we looked at those plots. You have 3 by 3 masks. If you go long enough, you can see everything. But if you only have a few layers, you can only look locally around you. And so you can do something like that where you say my Z is going to capture the global structure because it's not able to capture it at the end. And then at the end, the local things I can fill in by having a pixel CNN with just a small number of layers that can make things correlated close to each other. Of course, Z loses some information in, but maybe that's not what you want in Z. Maybe what you want in Z is the high-level stuff and the details, the detailed correlations you're willing to have happen at the end and not have a code for. Some people change the training dynamics. A lot of things being tried to make this work. And a bunch of references here. So another thing people look at is disentanglement. Remember, in the beginning we said we want generative model for sampling, for likelihoods, but also for representation. People said, well, what if I change my objective to put an extra term in front of the KL here? So instead of bringing Q phi z given x close to pz with some 1 here, normally this is 1. That's the original VLB. You make it a bigger number. You make beta bigger than 1. What does it do? It puts more force on your decoding distribution, your encoding distribution to map things into something that looks like a Gaussian. The more you do that, because a Gaussian, all its variables are independent, the more you are hopefully disentangling the latent variables. Because you now know that when you do that, when you try to decode, these variables are behaving independently, and so maybe you get better disentangled representations. And people do get some effects like that where they can find ways to play with the VAE to change skin color, age, image saturation more easily with the latent variables. Okay, so we covered a lot. We got 2 more things to look at. Last time, with flow models, we looked at dequantization. We said if we fit a flow model, we go from x to z. Or another way to think of it is we go from z to x, either way. Z might be some Gaussian, x some more complicated distribution, and we're mapping probability mass from z to x. But actually, x only has data. And so when you learn your mapping from z to x, where x is your data distribution, you might map it all into these like spiky spots, and that's not what you want. You want generalized very well. You might say, well, when I have a data point, you really should think of it as spanning an interval. And instead of thinking of it as just data point is in that real number, it's actually an interval around it. For pixels that go from 0 to 255, it would be a region of 1 around it, instead of just the specific discrete pixel number. We then saw that the way you can think of this, I have my log probability of the model training of my data. The way I can think of this is that my y is my original x plus some noise u. And what that comes down to is that then at training time, I just put noise on my axis and train with noised axis, and this will work out. That's what is sitting over here. And what this derivation showed is that that is a lower bound, and we're maximizing, it's a good thing, a lower bound. Putting noise in our x's is a lower bound on the original model, which actually assumes uniform distribution around x. So, and uniform distribution around x requires evaluating this integral. It's much more complicated, it's not easy to work with. So instead of actually doing this integral in that small interval, we're going to work with noising the input data to get something that's pretty close to it. But if we're going to say, oh, we're going to put a uniform distribution on our input data, why is uniform the right thing? Think about mapping. Underlying distribution might actually be slanted here. So why should I center a piecewise constant thing onto this when I'm training? Doesn't make sense. Turns out the same math we did, Jensen's inequality, all that stuff, you can actually, instead of putting uniform distribution there, you can put a variational distribution in there. Then apply Jensen's inequality where you swap the log was here and now is here. So log of expectation, expectation of the log. And you see that it doesn't need to be uniform. Any distribution that has the right amount of probability mass around that point, which is still the same amount of probability mass, but you can shape it whatever way you want, is okay. This gives you more flexibility, and so flow models can achieve better likelihoods using this variational inference trick that we couldn't really cover last time because we didn't see all the variational inference yet. But that's one of the things that's under flow does this to get better results. Look at it here. Green is the full model, and then dirty green, or whatever, yeah, I don't know, kind of other kind of green is uniform dequantization. It's a pretty big gap. So the assumption that you would uniformly noise things is a pretty big assumption. Instead, now we will learn variationally a distribution that tells us how to put noise on the discrete variables, sample with that noise, train, repeat, and get much better likelihoods. Let's see, last thing is mutual information estimation. This has, in some sense, nothing to do with what we covered so far, but the methods we saw allow us to think about this. What is mutual information? It's this thing where, well, take a step back. What is entropy? Entropy is a measure of how uncertain you are about a random variable. So random variable x, if I tell you nothing about x except for the distribution, but I don't tell you which x I sampled, how much uncertainty do you have about what I sampled? For uniform distribution, entropy is large. For peak distribution, entropy is much smaller. For Gaussian with small variance, less entropy. Large variance, more entropy. If you have multiple variables, you can also think about the conditional entropy of x given y. If I already observed y, how much entropy is still in x? You could imagine that, for example, if I ask you something like, what is the middle pixel value in an image? The middle pixel of an entire image, megapixel image, might be like, yeah, I don't really know. I'm going to guess something. High entropy. If I give you all other pixel values, there's only one pixel left to fill in, your entropy will be a lot lower. Your conditional of that one pixel given all the others is pretty small entropy. Turns out that mutual information between x and y is defined as tries to capture how much overlap is there between me telling you x and me telling you y. What's the overlap in information? Is the entropy in x minus the entropy in x once I know y. So why is that? Entropy left in x when I know y is the stuff that y doesn't tell me anything about. And so then this is all the entropy. The stuff that y cannot tell me about is subtracted out. So what's left is the thing that y could have told me about. Same thing here. This is all the entropy in y. This is the entropy in y. X cannot give me the answer about y. And so subtracting that out gives us mutual information. We'll see more of this when we do compression. But the reason mutual information is interesting, or could be interesting to you, is this. Usually people say I have two variables. Let me look at the covariance and see how they relate to each other. Well, certainly covariance says something about that. Covariance of 1, 0.8, 0.4, 0. X tells nothing about y in this plot here. Negative covariance, negative, negative. And so it goes up to -1. That's the extreme here. Okay, so it's correlation actually. So then here we have 1, 1, negative 1, negative 1. And then here we have all 0 correlation between x and y. So x, y, 0 correlation. When you look at it, you say, well, if you give me x, I can definitely tell you something about y for many of those, but just not first order. The first order correlation, the expected value of y given x is always 0. No matter what x you give, the expected value for y will be 0. But there's a lot of details still. When I give you x, and x is, if I have an x that's here, well, y is going to be somewhere here. But an x here, y is going to be there or there. Expected value of y in both cases is 0, but there is actually information in x about y. So mutual information x, y is not equal to 0, but the expected value of, well, in this case, really expected value of y given x is actually 0 no matter what your x is. So mutual information is something you might care about. There's a few methods that look at this. We'll, in 2 weeks, see Infogan, and even later, we'll probably see CPC in 3 weeks. It comes up in intrinsic motivation and reinforcement learning. What does that mean? You want to learn about something that you want to go explore, so you get information about something you care about. So you want to find, essentially go see a state that tells you something about how to improve your policy. The reason it comes up in this lecture is this thing over here. Mutual information between z and x, hz minus hz given x, can be written this way. That's just writing the definition of conditional entropy. After we've done that, we can expand this thing into, well, we add and subtract the variational distribution. After we did that, what happened here? That doesn't seem right. Oh, it's plus KL. Got it. So it's a plus KL happening, plus some kind of KL, which leads to this. And so what we see here is that we have a bound of the type that we've worked with. So the terms that disappeared are this here became the KL. So what we see here is we have the mutual information is bigger than or equal to, often we want to maximize it. So we have a lower bound on the thing we want to maximize. Often the prior for z we keep fixed. So z might be a Gaussian or something. We don't really change it. So this shows then is that this thing over here, to maximize our mutual information, comes down to being able to train a good classifier that goes from x to z. So as long as we can train a good classifier from x to z, that's this loss over here, we will have high mutual information between z and x. Assuming, of course, that we do not change the entropy of z, because it's very easy to get a good classifier from x to z if you just make z constant, but then your entropy will be very bad. Assuming you have a fixed entropy for z, then just training a good classifier from x to z will maximize your mutual information. Why would you care? Well, that would be a way to ensure, let's say you have, a pretty rich decoder, autoaggressive decoder, but you want your latent code z to still have information. You could add a loss term where you want to ensure that you have a good mapping from x to z with this classifier while maintaining high entropy for z. Okay, that was just a bit of an aside there. These are the references for today's lecture. And your homework 3 will come out, well, 2 will come out this week, 3 will come out in 2 weeks, and it will be all about this lecture. All right, see you next week.